Hello everyone, my name is Weston Turner, and today I'll be talking to you about modeling rotorcraft maneuvers using machine learning. This is my capstone project for Data Analytics 670. Here's a big picture overview of what we'll be talking about. Talking about a brief description of the projects, the goals, players, KPIs, going over the description of the data set, and then we'll talk to the strategy of the data analytics techniques that I'll be using, lessons that I've learned up to this date, and then the immediate next steps that I'll be taking in the coming weeks. So a big picture overview of this project. It was requested by the FAA to do a data analytics investigation into rotorcraft maneuvers. There's a broad base of data already on fixed wing, so airplane maneuvers, but there is lacking data on rotorcraft helicopter maneuvers. So the FAA has put together a data set, and they're looking for us to analyze that data set and come up with ways to identify and classify traffic patterns or other type of maneuvers. I'll be specifically looking at the traffic patterns. So you can see on the right side of the slide, it tells you what a traffic pattern is. If you're not familiar with that, it's basically comprised of different legs, and it's how a rotorcraft or a fixed-wing aircraft maneuvers around an airport, usually used for training purposes, so you can get multiple takeoff and landings. So this project can we look at classifying those traffic patterns and basically using a combination of high-level filtering and machine learning techniques to look at some time series data and derive what specific maneuvers are occurring during a said time period. The overall goal of this is to increase automation in and out of the cockpit. So inside the cockpit, the pilots can be notified if they're not achieving a desired maneuver correctly, and then outside of the cockpit, air traffic controllers, tower operators can all be notified if a maneuver is not going to plan or just what maneuver an aircraft is performing. This could give them better separation of aircraft, give them abilities to detect collision alerts a lot earlier if they can quickly identify what type of maneuver is occurring. The team specifically for this project is currently comprised of 3 students from UMGC, all having a different slightly aspect of the data they're looking at. I'm looking at traffic patterns, someone else is looking at approaches, and then someone else is looking at something called short stops, basically kind of hover approaches. And then the FAA also has 2 experts and data scientists that are helping us to look at the data and take or get the correct data that we need. For the project itself, there's going to be some key performance indicators. So like I said, I'm looking at traffic patterns. So the main indicator that I'll be going off of is what percentage of the data that is actually a traffic pattern is correctly labeled as a traffic pattern. This is important because in order to identify it, present it to the pilot or the controller, we have to label it correctly. So that's the true positive ratio there. And then the second KPI is the false alarm rate. So in aircraft, often if you have a false alarm, it is more situationally SA, so we call it SA degrading, than not having an alarm at all. Having an alarm go off can often lead to a pilot or a controller averting their attention when they don't need to do that. So a low false alarm rate is pretty critical to making a good, having a good method to analyze this data. So that's the second KPI. The third one is what is the required processing time or file size for a given method. So each method may have a level of complexity. The desire is to have the lowest complexity that still achieves KPI 1 and 2, and also has a relatively low file size, so we're not overtaxing a specific system. So if we have a low processing time, low file size, then we could probably put this anywhere to include on aircraft, in control centers, wherever we need to use these algorithms. The last KPI is how easily attainable the input data is. So I'll go into where the data comes from, but a lot of times some of this data is not going to be achievable on all aircraft just based upon how they record data. Not all aircraft record all the specifications that are in the many lines of data in this data set. So we're looking for something that's fairly easy and to have across all type of rotorcrafts. For the goals of each specific KPI, you can see those lists are there. For KPI 1, like that to be above 90%. KPI 2, false alarm rate needs to be below about 5%. And then KPI 3, I declared it relatively low, i.e. it's out of all the different models that are presented, the one with the lowest KPI 3, all else being equal, would be the best choice. And then KPI 4 needs to have a low number of variables and easily attainable variables. If we require a ton of variables to make an accurate prediction, then it's probably not realistic for all different types of rotorcraft. You can see what it might look like on the right side of the screen here, where we have different models, each with their own different KPI scores. What I really wanted to highlight here was that Model 3 looks like it's performing the best with a high KPI 1 and a low KPI 2, but the required processing time is fairly high. So what might happen here is somewhere between a Model 3 and 4, where you still have a low KPI 2, but a much lower processing time. Go back and look at some type of way to get in between those two and modify it slightly. So the processing time is important, so we can fit this on a variety of systems. Right, for the data set itself, the data is based upon outputs of simulated rotorcraft flights. So we're just looking at simulator events here. All that data is then fed into a computer the FAA has, and they have a system called the Rotorcraft Analysis Recording Database. It's going to take all the inputs from the simulator and basically convert it into a standard output type, and that output type is what we're receiving for this project. Important to note is that output database, the ROR database, can also take in-flight data recorder. So on the right side of the screen, you see what a flight data recorder might look like. Basically, it can take inputs from anywhere on an aircraft or rotorcraft. It looks at the position of the throttle, the amount of deflection of each flight control surface, a variety of factors. It could have a robust attitude, heading, and reference system, which is basically accelerometers in it. All different devices that could measure specific parameters on aircraft. One like that might have a very long list of things it's recording. There might be some simpler ones that are another rotorcraft that have a far shorter list there. So it takes in all that data either from the ROR database, takes in all that data from either a simulator or the flight data recorder, converts it into an output, and then basically it's all time series data in the ROR database. The specific files that we have are recorded at a rate of approximately 40 hertz a second, 40 hertz. So there's a lot of lines for each second there. Most flights have about 40,000 observations for a 10-minute or so or 20-minute or so recording. So a lot of observations. Currently we have 20 to 30 flights that we're looking at. That's about 1.5 million observations. Equates to about 2.5 gigabytes of data to sort through there. And that's with all the observations and all the features for everyone. The important thing here is that, like I said, because of the way that the database is structured, it takes in all the inputs available. Not all the features that are on there are very useful. I went through the list and I basically looked at the different features, what might be useful to predict the specific maneuvers that we're looking at, and about 37 out of 108 are actually useful and realistic to obtain. I'll show on the later slide how we're grading that, but it's based upon my experience as a pilot and what is actually going to make a difference for predicting maneuvers. All right, so it's a little bit more detail on this. So yeah, the simulator itself is going to run on X-Plane 11. They have what's called data reference exports. So pulling from the simulator live, and that database is then loaded into the ROR, and that is what we're getting on the CSV files to input into our scripts there. The real world flights would also go into that ROR data converter, and that would all be the same data that comes out. There might be some more missing data if it's a real live flight, just based upon inconsistency there. But for either a sim or a flight, the output is going to be the same. So it's important to note that whatever we develop here, we can port over to a real flight because it's all going to get processed through that ROR data converter first. All the data that comes out is a mix of float, string, time, Boolean. There's location too for lat long in there. So all different data types. Most of it is fairly complete, just based upon the simulator data. And like I said, all the variables have values for the sim flights. Now, some of them are 0 or not usable, but that may not be true for real flights. There may be gaps in the data, so you'd have to do some potentially more data cleaning there if you're using real flights. It's It's one of the reasons why we're sticking to simulators for this, just because to develop the algorithms is a little bit easier with that type of data. Like I said, I'm a 20-year pilot, so I looked at these features and I divided them into different categories there, the difficulty to obtain, so easy, medium, and hard. Easy being that it should be on any aircraft, medium, most aircraft, and then hard. Only special instrumented aircraft would probably have those types of features. And then usefulness, high, medium, low, and none. High meaning that it has a high probability of detecting and predicting certain types of maneuvers. Medium and low, you can just basically go down from there, and then none being has no predictive anything to do with any of this type of maneuvers. An example of that is one of the features is the current comm communications channel that the aircraft is on. So who they're talking to, that is in a frequency, so it really has no bearing on what type of maneuver they're performing, but it is included in the data set. You can see on the diagram there the high level, how I kind of described how that goes into the Aurora data converter, and then the output goes into the ELT script that I'm using in Python. So that will combine and window the data, and then I will use the machine learning models in Python and the ensemble models in IBM, SAS, EM, to basically have a final output that will be the visualizations and potentially some Python visualizations as well. For the data prep requirements here, you can see that I just took a snippet of the data. When you initially look at the data, it looks complete and like there's no missing values in there, but because it's time series data, you really have to be careful and look at it. There are a few gaps. So if you look here, you can see that basically it jumps from 1539 to 1544. It does that quite a few times where it's jumping, and what I think is happening is they're pausing the sim in between certain events, talking about it, and then continuing. So when you window the data, which means basically breaking into different time slices, you got to be careful of this. And I did account for the breaks in time here. I'm not going to go into detail on how I did it, but the algorithms do account for that. There's also non-traditional outliers. So another thing that commonplace in sims is to pause the sim and then drag the aircraft or rotorcraft to a different location. So what could happen here is the time could be fairly compressed, and then the sim might be repositioned significantly, which could change a lot of the values significantly right away. Basically, I can use high-level filters to remove the physically impossible data. So if an aircraft moved in excess of a certain distance over a short period of time, it could be deemed impossible, so just based upon physics. So those certain data there could be removed and then continue from there. So based upon that data, basically then I'm going to use a windowing approach. It's called sliding window method to reduce the time series data into about 180 second chunks. I'm using 180 seconds, 3 minutes, because that's the standard. I think around 5 to 6 minutes is when it takes a rotorcraft to do an entire traffic pattern maneuver. So we're going to look at basically half that to make a decision whether it's in it or not. And those 180 second chunks are basically every about 50 seconds I'm taking one of those. I'll show in the next slide what that's going to look like, but each of those windows is going to have derived variables in it instead of previous values. Some traditional windowing approaches look to take the previous value at the previous window and incorporate that into one line of data. I'm kind of going with slightly different. So yeah, I'm going with a slightly different approach here, and I'll talk through it. So it's basically take a certain window of data and then do an operation on that data, and then move the window over, and then take another observation there and capture that data. So you can see how it would work through the data here. The 180 second window that I'm using here should encompass most maneuvers that are occurring during the data set. The key here is that it's going to reduce that 2.5 gigabyte input for all of it into about 2.5 megabytes. So it's a reduction in size of almost 1 to 1,000. I'm doing that because, again, I'm not considering all of the different features, only the ones that are actually useful. On the right, you can kind of see how the input through the time series is going to be divided up into all those windows and how they're going to overlap. So unlike the little step through one I showed you at the beginning there, the windows here are going to overlap. So you'll have multiple windows looking at each time slice there and kind of comparing those. And then the output to that, after it goes through that algorithm, should just be each window and then the derived variables that come out of that. So each derived variable is specific to a parameter there. So just an example here for a heading, I can derive out of the heading basically the start and end heading for each maneuver, each time slice of that window, and then I can get the total heading change out of that. So you may think that those are always going to be the same, but as you can see in this example, the start and the end heading, so the start heading would here be north, the end would be east, and the total heading change would be 90 degrees. On this next example, the start heading would be east, the end heading would be east, but the total heading change out of this would be 180 degrees. So it would describe a different maneuver. So by combining these variables and basically getting the derived variables out of it, we can describe maneuvers without having to look at every section of the time slice. Some variables have complex transformations like that heading example I gave you. Others will be relatively simple. I just have min, max, average, standard deviations types of derived variables out of all of those. The specific strategy that I'm using to analyze this data, basically I have three kind of paths on this: the required path, the desired, and the optional. You see the diagram there. So the required data is basically taking all of this compilated time series data and getting an output of when a traffic pattern is occurring. So that's the min kind of goal there, and realistically that's maybe the only goal that's achievable in the time that we have to do this project. Kind of a desired goal is a output of the phases of the traffic pattern. So if you remember on the first slide in there, I showed you the diagram of the traffic pattern and had different phases of it. So there's the upwind, crosswind, downwind, legs, base, and final. So if we can identify those, it might provide slightly better data to the overall FAA program there. And then the final one, which should be optional if I have enough time, is grading the specific phases of the traffic pattern based upon a known type of parameters. The overall strategy, I'll have three distinct methods. So the first one might just be basically taking the windowing, applying it to non-labeled data, and then using advanced filtering for specific parameters, and then being able to derive what is going on during the maneuvers. That's actually a fairly robust way of doing it. But since the focus of this course has been on machine learning, I'm going to take that a step further. The next method will basically be windowing using labeled data, and then using machine learning to derive when a traffic pattern is occurring. And then the final method is going to be combining the both. So basically using advanced filtering and machine learning together, what I'm going to call maneuver specification scores. So those are kind of a way of filtering. So basically you can see an example there where I took an altitude factor. So if you can read all those, but if there's certain regimes where the aircraft's operating in each window, it'll give it a score. And then the machine learning technique, you combine that with other variables to predict what is occurring during the time periods. So I think what we're going to get from this is that using a combination of human input and machine learning is most likely going to produce the best results, but we'll see. There's potential that machine learning on its own could do just as well. So far, the biggest lesson that I've learned is how to convert time series data for machine learning. So lots of research on this. A lot of it has to do with basically following stocks or basically calendar type data, passenger counts over in the airlines over months, but not a lot of it has to do specifically with the time series type of data that I'm looking at. There's many different methods. There's windowing, differencing, detrending. Windowing we already talked about. Differencing is basically kind of taking a known value and seeing how it varies over time. Detrending, also an interesting one, where if you look at the graph on the right, you can see how it has an upward trend. But if you take the kind of linear plot of that and then get rid of that upward trend, you can see other variations in it. So that's useful for, again, some type of over time analysis, maybe not specifically in this, but basically learning how to do each type and knowing what each type is good for and what each type is not good for is one of the biggest takeaways I've had so far. The second big lesson I've had is how to write useful Python scripts for extract, transform, load. So it's very powerful to be able to do some really custom scripts there instead of just kind of your standard ones that are offered in some other platforms. What I actually really like is PyCharm. It's a really powerful IDE for Python, and it has basically real-time debugging and data views, so you can see what's going into each variable along the way. Have saved me a lot of time. You can look here where I have like what I'm using for the altitude data and how I got the lambda functions in there to derive some of those variables, and it's pretty user-friendly. So that's the second big lesson so far. And then the final lesson is that I think for this project you need a realistic scope. So I talked about the desired, required type of and optional, but I really think a lot of times, like in this specific project, the FAA has been working on this for 6+ years. So you got to have a realistic scope in mind, and you need to have achievable goals, because if you try to go too far, you won't get anything done. For the next steps of this project, the biggest next step is that most of the data is unlabeled CSV files. Like I talked to, it comes out of the Aurora database. And then for each of those specific files, for some of those files, there's handwritten flight logs. So you can see an example of what a flight log might look like. It's just a write down of the times and what's occurring during that. That's not standard output for most pilots. Most pilots could recount that after flight, but most pilots don't keep a detailed flight log like that. So this is just done for the simulators. So basically I need a way to take that handwritten flight logs, input it into the current database, and merge it so the labeled sections of time are correctly labeled what's going on. I have some ideas, but it's going to take a little bit of work there. The next, I need to create some data visualizations. Basically, I'd like to plot a graphic of what a traffic pattern looks like with the specific data, and then overlay that with the derived variables and how they're changing during time. And then I need a variable importance plot, basically seeing which variables are the most important so we can get rid of even more of them and aid in minimizing the processing time required. And then finally, select the appropriate machine learning techniques here. So like I said, I'm going to start with IBM SAS-EM to try to narrow down what is working the best, and then use Python. That Python's been requested by the FAA. It's the final output. So use Python for whatever is working best, and then run that through. Here's the references that I used for this specific presentation, some of the diagrams, some of the graphics. And then are there any questions at this point? Feel free to email me. I would put that up there because not to generate questions, just how robust different types of maneuvers can occur in the traffic patterns. So just a lot of different options there. So kind of a difficult problem to capture. All right, so that's the presentation again. Email me with any questions you have.